Let's get started on time. So this one is a pretty exciting project compared to the previous ones because this one is making the IPGA chip more intelligent. Because right now you are embedding a CPU into it instead of just a static logic, or even it's a sequential logic is still very simple, just transitioning in between all the states. And I was thinking about this kind of CPU. The name is called KCP SM6. It was invented by a person worked for Xilinx, but Xilinx was acquired by AMD a few years ago. So that's why when you are downloading the Vivado software, the compiling tool is all from AMD website. So this is probably IP for AMD right now. It's very simple. It's an 8-bit CPU. Compared to the other, even Arduino CPUs, it's just way simpler, like 100 times easier to these ones. You can see the architecture of the CPU is being drawn in this picture. And this is just one page from the user manual. You can access to the user manual over here. Okay. It could be confusing sometimes because this is a newer version, was launched in 2014. It's already 10 years ago, but it's the newest version of it. It's called Pico Blaze, the Pico Blaze. You can see you can use a Pico Blaze CPU for all these different types of Xilinx IPGA boards. It could be Spartan 6, Vertex 6, and 7 series. So remember, when you started the new project in Vivado, which one did you select? Arctic 7, so it's a 7 series. So keep in mind, ours is 7 series. So this will be applied to different places in the program later on. So it's good to know that the IPGA you guys are using is the 7 series IPGA. But you can also buy different IPGA boards from Xilinx, but now AMD, with the different chips on it. And it's very interesting, KCP SM. So the name for it is actually constant coded program, like I forgot, small microcontroller or something. But the name of the inventor is K. Chapman, is also KCP. I think probably he named it intentionally. And there's another version called KCP SM3, which was launched probably 5 years before that, which is probably like 2009. So that's why you can see from the textbook. So this class required 2 textbooks, right? I already required 1, but the other one is optional. So the required one is all the materials that I put on the tutorials of this class. So I just translated everything from the textbook to the tutorials. Yeah, I've been working on those examples from that textbook throughout the semester already, but you just probably didn't notice that. But anyways, so all these materials are from the required textbook. And there's another textbook which is really a popular one in the IPGA field. A lot of institutions are using that textbook, which is Peng Chu's. I think this is this guy from Hong Kong, I guess, and now is a professor in Iowa University, or I forgot the name of it. It's Iowa State or University of Iowa. Anyway, so that book is pretty good. Give a lot of examples. So all the upper level examples in this class, including the soft core, the SPI. I used to have I2C included, but I just realized we don't have enough time on it. And USP probably, all these examples are from the Peng Chu's textbook. But all the previous ones are relatively easier. These are from the required textbook, okay? If you didn't purchase it, which is fine, I think I have some of the pages compiled into a PDF and uploaded to the tutorial. So you can see you can find the code for a few examples in this tutorial from Peng Chu's textbook. But one of the issues is the Peng Chu's textbook used KCP SM3. It's an earlier version of the Pico Blaze microcontroller. It's really annoying. So when I was trying to working out all these examples, that's probably 3 or 4 years ago, trying to put or developing this course, I found out, so the IPGA we are using is a newer IPGA, but the Pico Blaze core, the KCP number 3 version is too old for the IPGA, but we cannot just afford another 100 or maybe 20 new boards for students. So I have to use the Arctic 7 boards, but with the new examples. But the textbook didn't provide the examples using that KCP number 6 version, which is the newer version we're using right now. So I have to, fix a lot of issues with the existing code from the textbook. Luckily, all these kind of bugs are already fixed, so you can directly use examples I provide on the tutorial. I think for this lecture tutorial, it's really straightforward, no-brainer pretty much, because all the examples are already provided. So the only thing that you need to design will be the very last one, I think number 11, but all the rest are just a copy and paste. As long as you know how to do it, it's going to be a different workflow compared to the IPGA compiling, like generating the bit stream and uploading to IPGA. So now we are actually designing an SoC, which is a system on chip. It's the easiest version of SoC you can make on the cheapest IPGA on this planet. So in the future, if you are hired by a company like digital design company, Samsung or any Qualcomm, they require you to use like ARM's CPU to design SoC for the CPU for the phone or for the laptop. It's a very similar workflow. It's just to put it's just a V file, .v file as one of the modules you include into a top module, and then adding all the memories and instructions to it and compile it into one bit stream and upload it to IPGA. So IPGA will be the final chip to test, right, before you tape it out as a ASIC. So it's going to be pretty much, it's very close to the final product as a digital chip, but it's going to be on IPGA instead of ASIC. Okay. And I was also thinking about, can we tape out this Pico blades? I know it's worthless. Why do I have to tape out the Pico blade? It's an 8-bit microcontroller, but however you can think about it, if this is a application-specific IC, for example, you want to place it in a certain place, for example, someone is doing a biomedical engineering application or experiment. They want some like implanted CPU to provide stimulations to the brain of the rats. So whenever they want to embed a little CPU to the inside the body of the rats or into the brain of the rats to provide some stimulation or building some neural interface for a research project, for example, to probably treat Parkinson's disease or Alzheimer's disease, things like that, right? If they have to purchase a core from ARM, it will probably cost them $20,000 or even higher. However, if they just use an open source core like the Pico blades, if it's simple enough, just doing a simple loop or jumping, some conditional statements, I mean, Pico blades is good enough. Why do I have to use a ARM core or like any other super expensive ones? A lot of them are not available. If you have to purchase them, you have to, pay a lot of money to get a core. So you can build an open source microcontroller by yourself instead of purchasing from somewhere else. Or you're thinking about why do we have to make an ASIC instead of just buying a Arduino chip or STM chip? Because sometimes this is really portable and you don't have so much area in the brain. So I want to target one specific area in the brain of a certain area to stimulate or receiving signals from the neurons, and it has to be super tiny. So it's better to just use a silicon chip instead of putting everything into a package. You don't have the space to put the package in it. But if you just need maybe you can design a very simple, very small PCB board, tiny piece of PCB, or it can be a flexible plastic film PCB version, but on the plastic film, flexible. And you have a silicon die, you can design the silicon die in probably the area of 1 millimeter by 1 millimeter. Okay, that's a chip. So instead of an Arduino chip, it's just a 1 by 1 millimeter. Okay, and then you can solder that little silicon chip onto a flexible PCB film, and adding some like crystal and other peripherals onto the little flexible PCB film. You can build a super tiny system that is able to be implanted into a certain area. It could be the brain of the rats, sometimes doing some neural interface or providing some stimulation, or it could be like a pacemaker or something else, or implanted sensors or actuators. Could be super tiny. So that can be a potential application for ASICs you can think of, and this open source is totally free. But I have to, sell it for a commercial purpose. Probably have to get a license from all these vendors. But for prototyping, starting up the company, so the PicoBlaze or other open source cores are all good options for it. So this tutorial will teach you how to go through the entire workflow from nothing to a little microcontroller. So it's not going to be like programming microcontroller in other classes. So you guys are actually designing a microcontroller on the hardware and putting a simple program into it. It's pretty exciting work to do. In the future, we're interviewing with any digital design companies. You can tell them you have some SoC design sort of or integration experience. With what? With PicoBlaze. It's okay. PicoBlaze and Xilinx FPGAs. Still, you're designing a SoC or microcontroller. Okay. The user manual can be found here in this link. Keep in mind, it's number 6 version, not 3. In the textbook, it's number 3, but here we're using number 6. It's very simple. All these are the registers available for you. You can see from S0 to SF, 16 registers, and have another 16 registers in bank B. So totally 32 registers you can use. And flags, carry 0, I'm going to show you what that means in the tutorial. And you don't really have to care about all the rest of it. It's just directly doing all the computation for you. So what you are going to program with assembly using this microcontroller is going to be manipulating all these registers and take care of all the carries and zeros like flags. And also need to know the port IDs. We probably are going to use the port 0 most frequently and show the results on the LEDs or get input from the switches. So these are just examples of the specs of the number 3 version, I think. And same to this diagram. So you'll see different diagrams of the number 6 version, but I just don't have I couldn't find the diagram because that's the only textbook available on the market. I was thinking about, I have an idea 2 years ago when I was, when I fixed all the issues from the textbook, I was thinking about selling all this code to the author in order to get the newer version of the book, because this is the only place available on this planet have the number 6 version for this FPGA, because I fixed all the issues. Think about that, okay? Selling all the code to the author. It's not possible. But I don't have the time to draw the diagrams. If I do have time or there's a motivation, I probably can.
So what you're saying is I should draw all the diagrams and then you'll bring it back and sell it to them.
If you want to do it, right? Why not? It's a good contribution. I don't have to use the old, snapshots and figures here, which is confusing. Okay. So the registers are just the memory banks. How many bits are there? 8, right? So most of the simple microcontrollers are just 8 bits, including Arduinos. 8 bits. So that's why the registers are 8 bits. S0, 8 bits. So all the registers in the memory bank, every single one is an 8-bit. And a program counter. So after you start the program, the crystal is going to drive the program counter to take out the instructions in the memory one by one and send it to the. So taking data from the register and do the operation according to the instruction, okay, and send the data back and forth. That's how the CPU works. So it's good to see. Most of you guys are in the microcontroller class right now, taking a lot of assembly programming. So the assembly code in this class should be super simple for you guys, I think, since you have the experience over there. These should be like no-brainers. But for the people who didn't have any assembly programming experience 2 years ago, it was pretty hard. But now it should be very easy. But you took architecture, so it should be simple. Are you in microcontroller as well? You are, okay, cool. You took architecture, so cool. Should be simple, okay? So the instructions are here. So when you are learning the architecture, you learn the instructions because they design the hardware, then they have all the instructions available because they have the hardware to do the job. And let's get into these simple ones first, and I'm gonna show you some examples later. So AND is a bitwise AND, easy, right? So two registers holding two 8-bit numbers and just doing a bitwise AND operation, and the final result will be stored in SX. So you can see that there's another option here. It's called carry. It's a flag. It's a certain 8-bit register or a space holding the carry, and you are wondering like, why do we need a carry for the AND operation? It's just a flag. It's just over there. So for here, it's not doing anything with a carry bit. So you can see it's giving a 0 to it. Okay, so AND, you can add a constant to it. So the constant, the 8-bit constant as well. You can do an OR logic, an XOR as well. Okay, so we don't really use a carry for these operations, but we'll use carry later. Okay, just pay attention to it. Adding without the carry, so just adding these two values in the two registers and put in SX, adding no register, no carry, and now see it's adding with the carry. So I have to add a carry into it. So in that case, so carry is a register, it's shared. It's not a just specific carry for that kind of operation. You need to know that. Because if you look at the architecture here, these are the registers and these are this is a carry. It's not a register, but the carry register and the 0 register is holding a value in it. Okay, it's just a memory space. And it's unique. It's just a 1C and 1Z in the CPU. Okay. And there's a compare instruction. So what compare does is, if these two registers are equal, give Z a 1, give C a 0. So Z, remember, you have a Z and C in the architecture, in the memory space. So Z is a 0 flag and C is a carry flag. These are just the two 8-bit flags. Just memory space is similar to the register, but doing something different. Okay. So if we come back to compare, okay, so just follow what the instruction does in here and use it to serve your purpose for the program. So now what the compare does is, if they're equal, it set the flag in 0. So if they are equal, 0 will be 1 and C will be 0. So I put a ZC here, but actually it doesn't have that kind of thing. I just showing you ZC will be 1, 0. Okay, but you have to use them individually. So can you think about, I don't know if you have done that in microcontroller class for the assembly, but why do we need a flag? Why do we need a Z and C there? Why do we need to know that? So how it serves our program? So when you program in C, right, you can do if. But can you do if in assembly? I don't know if in are they? Yeah, I do branches, right? Yeah, so branches. So if that one's 0, then you branch or jump. Okay, so you can use that one as a condition to make a jump or branch in order to do the if statement in the C. You couldn't do if in assembly. That's how you do it in here. Okay. If you see a 1, right, you can jump. So I'm going to show you how the jump works over here. So jump, NC. So NC means, so C is not 1, which means C is 0. So this here you can look into the C in order to make a judgment if you want to jump or not. So jump C, if C is 1, right? If you got a 1, then you jump to AAA. So AAA will be another section of the code. And have another way to jump, which is called colon return. So colon return, so it's going to return back and execute the instruction right below the call instruction. Okay, and there's another interesting instruction called test. The test instruction. So what that does is it's doing a bitwise AND operation with the two registers. And if you get a zero, then Z becomes 1, otherwise Z becomes 0. And at the same time, it's doing a XOR logic for all the bits in the result. Are you familiar with this kind of operation? It's doing XOR for all the bits. What is this one doing? Is that similar to something? So you are doing XOR within the 8-bit. Better. It's a parity generator, right? It's a parity bit generator. So you can use this instruction to create a parity bit. So is this a odd parity generator or even? So if it has odd number of ones, C will be 1 or 0. So 8-bit binary number, you have odd number of ones in there. The result will be 1. So it's creating an even number of ones, right? Eventually. Is that called an even parity generator? Forgot.
I feel like I remember being switched. Like the odd parity generator was like the evens were 1. Because it generates the bits.
Yeah.
Generates 1. Okay.
Yeah. We know how that works, okay? Doesn't matter. The name doesn't matter. You can always explain to the whoever interview you. So that's how the test works. The test does 2 jobs. Okay, keep in mind, it can be in the quiz. So the test instruction does 2 jobs. One is the bitwise AND operation, and second is it's a XOR logic for all the bits, right? So that's just giving you an example that you can see all the details, the technical details of the instructions in the technical menu that I have the link on the top of the tutorial. You can see even the structure of the circuits, even though it's not exactly the same circuit in the hardware, but you can see it's doing a bitwise and showing and giving you 2 flags at the output. Okay, and there are some shift and rotate instructions. It's pretty interesting. It's shifting and adding a 0 to the LSB and adding a 1 to it and rotate it and put a C back to LSB, just doing all kind of things, trying to let you program some complex programs to do difficult tasks because you don't have a C, it's all in assembly, so all this will help, right? And load and fetch could be different. Sometimes it's called store in other assembly architectures, but now it's load. Load is, so when you have a load and fetch, it's actually interfacing with memory files. So you can load the data from memory to a register, or you can fetch it, which means you are sending a memory data to a register. I also have store. So store is going to be store something into the memory. Okay, and input and output. So these are the instructions directly interfacing with the hardware. So keep in mind, these are not just pure software. These are able to interface with the ports. Okay, so for example, if I put a 0, 0 here, which means it's a 0, port 0. Okay, and in your test bench in a Verilog, you should put the port ID and interface the port ID with the switches or LEDs in order to communicate with the hardware. Okay, so So when you are doing input and output, keep in mind, it's dealing with or interfacing with hardware, not just software, because it's, you can see it's a port ID. So ISY is interfacing with the port ID. I'll give you some examples. Okay. But I think it will be helpful to look at the workflow first because it's totally different compared to the previous ones. How do we do it? Just make the question simple. All right. So first, there's a zip folder which is accessible from this link. Okay. Pay attention to this. Okay, important. You can download a folder and it's going to show all these kind of things in the folder. That's the official KCP-SM6. All the files are in there, and the KCP-SM6.exe. So if you don't see the extensions, you should go to the folders like view and options and to display all the extensions. So the KCP-SM6.exe will be the assembler which convert your assembly code into machine code into 1 zeros. Okay, so in that case, I was thinking about, can I really design a CPU by myself? I think you could, if you can write up all the Verilog, the hardware description language, and have to design the assembler by yourself, so which understands the assembly code and convert into a corresponding 1 zeros, so your hardware can understand it. So that's the only thing I need to do. If I want to design a CPU similar to Pico Blades, what I have to do is, design an assembler, because the CPU itself shouldn't be very difficult. There are so many open source ones. You grab one, you understand it, and then you can manipulate or change some of the materials in it. You can definitely design a CPU by yourself, but this could be a bit difficult to make. So this assembler, okay, you are not using everything in this folder for a project. You drag and drop your assembler to a project file. So assuming that you already created a project using RTX 7, the 7 series FPGA board, okay. So open up the folder, have all the files in there, and drag this and drop it into the project folder. Okay, that's the first thing you want to use. And second, you want to open up the Verilog folder, and it has 3 of the Verilog files you want to use. And the first one, KCP-SM6.v, okay, that's the CPU. It's just a .v file. That's the CPU. All right, it's a module you can include in your top module, and so you can include the CPU into your SoC design. Definitely drag and drop this one to the project folder. And the second one, you can see it's an underscore template.v. So this one is not one of the design files you want to use, but the template.v provides the example code about how you want to program, how you can interface with the ports. You cannot directly use it because it has all the comments and things. So you want to open it up and copy and paste into your design instead of directly use it. So this one, the template file, provides you the examples of the Verilog file you can use. And the ROM underscore form.v, it's not a ROM file, keep in mind. It's not a ROM file, it's a format file which defines the ROM format. Okay, when you run the assembler, it's going to directly use it to format your ROM file. So the ROM file is a read-only memory, will host your assembly code. Okay, so we are talking about assembly code, the instructions you can use. So after you program your assembly code, you want to use assembler to convert it into a ROM file, because all the instructions will be stored in the ROM file and being stored in the SoC as a instruction memory, and then your program counter will keep counting from that memory and taking out all the instructions from there and for the CPU. Okay. So you need 3 files over here for your project folder. And you need to create a main.v file as a top module where you can include your CPU, your ROM. See, here's the CPU file. You name it CPU as processor. And these are something you want to change. So the port, I'm putting switches, just SW, that's a keyword, that's defined by a constraint file. So switches as an input port, and interrupt, I disabled it. So I'm giving a 0 to the interrupt, so it's not being activated. And reset, put RDL there, reading line, something I forgot. But anyway, just put RDL there, so it's not resetting. And sleep, put a 0 so it's not sleeping in the sleeping mode. It's not in the sleeping mode. And clock is the keyword, is a clock, 100 megahertz clock in the IPGA. So this is our top module for serving the V6 version of the CPU as a main.v file, okay? So where you can include all these parts, and followed by the program file, which is a ROM file, user ROM's file name. So you program everything. Let's take one step back. Where do we want to program assembly? That's my question. Where do we want to program assembly? Just open up a Vim file, okay? And just start typing in there. Very straightforward. Start typing in with your assembly code and open up your command line window, okay? And get into, so it's very similar to the Linux commands, just cd into this path, this directory, where you have the kcp.exe assembler in there. Make sure you have that file, you have the assembler in there in order to run it. If you don't have it, you cannot run it. So in the command line, get into the folder which has all the project files, including this guy, the assembler. And this is your assembling code of the program file. How to create it? I told you, Vim, okay, or text editor. Open it up and type your assembly code in it and save it as .psm. Okay, not txt, not anything else. Save it as .psm. So, didn't work? I'll take a look at it. Interesting. Yeah. Yeah. But did you have the ROM format, the ROM underscore form in there? Okay. Yeah, let's take a look at it. So if you run it, it should generate a prog program. I just named it prog.v file in there. It should generate that file in there. Okay. So that will be the memory file. Will be the memory which has all the instructions in it. Okay. So the runner converts every assembly code into the machine code and stored into that memory file, and you can directly use as a V file. You can include it into your top module over design, okay? And then you have a main module. The top module has all the Verilog, does all the connections, and your CPU, your program, you're ready to run it, okay? Compile it. So the first example is gonna turn on the LED if you turn on that corresponding switch. So there are more examples provided, including the square problem from the Punctual's textbook, which will have the square of each number and then add them together and show the result on the LED. I think all the code, everything is provided in here, just let you run through the workflow instead of designing everything at the very beginning. So learn it first before you do it. So these are the Verilog code you should include into the main module at the bottom, okay, to make the connections. And the CPU get the results at the port. So you have to, tell the SoC to connect the results to the LEDs. It's very simple, okay? It shows the results in the videos. And I have more examples here. So let's go through some of the assembly code in order, so if you guys are not familiar with it. So input, keep in mind, input interface with the ports. If I put a 00 here, which means it's actually connecting port 0 to the register. So whatever the register here is hosting, no, whatever the port receives at 00 port, it's going to send it to the S0 register. So in that case, if you connect the switches to the ports, for example, port 0, if you have a 0 for the switches and you are able to send a 00 to S0 register to the CPU. So that's how you can communicate with the inside of the CPU. And then load it. So you load the register, whatever the S0 receives, and you load it to S1 register, okay? And you add it to 13. It's not 13, it's not 13 actually, so it's 13. So all these numbers are hex, okay? And output. So after that one is being added to S1, you output S1 to port 0 to the LEDs. Okay, so it's going to show the results on the LEDs. And this shows you how to use a mask. So constant 03 can be loaded to this variable. And so the mask means it's doing a OR operation. For example, S1 is an 8-bit battery number, right? If it's being ORed with this number, what's going to happen? If S1 is any like 8-bit battery number, it's being ORed with this mask, which is this guy, what's going to happen? So what's this one doing actually? So what is this mask doing? Just directly tell me the answer. Setting the first 2 bits, right? Do we really care about the rest? No, because 0 or these are still the same number, right? So we don't really care. So are just setting the lower 2 bits. So in that case, if you output it, you'll see the lower 2 bits are always on. Okay, it's a good way to verify it. And also, I gave you example for this shift and rotating. So it's placing the 0 to the LSB. I can test it. And for here, it's a really interesting example. I think I should modify it. If you guys are interested in that, please do it. However, this example is probably not returning. So let's take a look at it. So it's forever gonna run forever. It won't if you don't return, right? It's just a number. It's just English. It's not a keyword. Okay, you have to return to forever in order to run it forever. Okay, so input, you take 00 port, whatever at 00 port to S0. Okay, and you have 5 and 6 for these registers, and you load the input into here and test what the test instruction does. Remember, it's a bitwise AND, right? It's a bitwise AND. It's also a parity generator as well. So it does a bitwise AND. Let's take a look at it. It's a pretty good tutorial. Seriously? Test. It's running a bitwise AND. Okay. Quiz alert. Okay, it's gonna be on the quiz. It's doing a bitwise AND, right? Bitwise AND, and send it to T, but T is not being used. It's been discarded. It's being assigned to T, but it's not being used at all. It's doing a bitwise AND. So if T is 0, then Z is 1. It's like an intermediate register, right? So if T is 0, then Z is 1. Otherwise, Z is 0. So which means if you have a 0 in it, it's setting Z because Z is a 0 flag, right? So we don't care about the parity right now, so we're not using it. Okay, let's go back to the example and take a look at it, how that works. It's a really useful instruction for Pico blades. Okay, so what this one does, so what is in S1? What is in S1? Yeah, port 0, right? So port 0 could be a switch. So you can think about you have a switch in the input, and S1 is going to hold your switch input. Okay, it could be anything because you can do whatever you want. Okay, so S1 is a switch. So what about 0, 1? So what is 0, 1? It's 7 zeros and 1 as LSB, right? It's a hex number. So 0, 0, 0, 7 zeros and 1 as LSB. So if I'm doing a bitwise AND, what is this one doing? What is this one actually doing? It's not still not getting to the point, but what exactly or essentially this one does? 1 or 0? Is it testing S1's LSB? Do we care about other things? We don't, because all the 7 zeros in 0, 1 will just reset everything, right? But what about the LSB in S1? No. So let's do this, okay? So if S1's LSB is 1, what's going to happen? So what's happened to Z?
It would set Z.
So
They're equal?
No. It's doing a bitwise AND, right? So if S1's LSB is 1, what's going to happen? Yeah, so the results LSB will be 1, but it's going to be a non-zero, right? So the flag Z will be what? 0. Okay. If S1's LSB is 0, what's going to happen? So Z will be 1. Okay. So this is actually testing what? It's S1's LSB, right? Yeah. So that's why I hate assembly, but you have to do it. I mean, in C you can do it very easily, but now you have to. So the purpose is to check S1's LSB, 1 or 0, right? In order to do something. Okay. So if it's non-Z, which means Z 0, you jump to testing. If Z is run this guy, okay? But however, keep in mind, what I saw in the video is actually not returning to here, because I'm using jump, not call, I think. If you guys have the time, please try call instead of jump and see if this guy will come back and return it. So it seems like jump, after it jumps, it's done. It's going to skip everything below it based on the result I saw in the video, okay? Could remember like a few years ago how I did it, but
so no matter what, we're outputting 0 to S2. What's the point of S2 in that?
So S2 is outputting to here, right? So it's trying to, so the goal of this one is to see if it's 0 or not, right? If it's not 0, if it's 0, it's going to run this guy.
Oh,
so output will be 5, right? If it's non-zero, output will be 3, S3. Okay, because S3 is 6. So it's going to be 5 or 6, depends on your switch input. All right. However, if you use call, if you replace this one with call instead of jump, and we are assuming that if you use call and return as a pair, and it's going to return, okay, what's going to happen to the result? Yeah, it's going to be overwritten by S2 all the time. And even though it jumps here, but you know the program counter is running super fast, you won't be able to see there's an intermediate like 5 display on the LED. oh sorry, 6 being displayed. Even though it jumps here, this is going to come back to here again and then rerun it. Oh no, it's going to return here, right? It shows this one probably with like 1 microsecond and then we'll come back to S2. I hope. Okay, if you can test it, I'll be happy to see the result. Just replace this jump and let me know, okay, in the report. Assuming that jump and return is not a pair, okay? If you put a jump, it won't return. That's what I saw here. Okay? It's not returning. If you use code, hopefully it's going to return. So you're always seeing S2 instead of S1 in that case. All right. So more examples. These are just the name of the sections. Not Z, is Z. All right. Testing, same concept. Test, it's a bitwise end. If I use a constant as O1s, FF, O1s, I'm testing if this guy is O0s, right? So if it's not 0, jump to here. If it's 0, jump to here and run these following instructions. And compare, it's a different instruction. So just follow whatever it tells to do. All right, and for that example. And number 11 is not given, but I do have a demonstration that shows how that works, which is actually counting the number of switches that are on and shows the binary results on LEDs. Should be easy to do, right? Think about it. And repeat the work from sections 3 to 11 and show the demonstration video for credits. There's the points. So this one is pretty simple because most of the code is provided. And we'll have a lab next week because this week is a VGA lab. The VGA lab is creating a little animation here with the VGA. We'll do it on Thursday, okay? Any questions so far? I believe next week's lab will be the soft core, will be more complicated, but a lot of fun as well. So next week will be the USB and then SPI, and then we'll do the course project. Will be the Yoshi's Nightmare game, I think. So this time I prefer, instead of letting you guys just duplicate it, right? I hope we can understand every single piece of the code in the game. I know it's pretty long, and I hope everyone can give a presentation on it, do some modification to the code. This time will be different from the one 2 years ago, because this time I already have a tutorial from Max, and he actually did a 3-week internship after the class in the summer. So he added a lot of peripherals to the circuit, including the joystick and Arduinos, in order to convert the joystick signal, use a joystick to control the little character in the game, instead of just watching it use the keyboard keys, which is not that fun, right? So we can use the joystick to control it. Any questions by far? No?